Welcome to Pharmaceutical Calculations, a conceptual approach, Lesson 30, Rates and Orders of Reactions, Part 3, First Order Reactions. Today's objectives are to learn how to recognize first order processes and use best fit equations from concentration time plots to determine drug initial concentrations. Now we know that this is C0, first order rate constants K, and half-lives that would be T1/2. Now, as a reminder, pre-required knowledge of logarithmic and exponential equations were discussed in Lesson 27 and were applied in Lesson 28 and Lesson 29. So please review those three lectures to make sure that you can easily handle logarithmic and exponential transformations. Now, if I am to describe a first order reaction using the differential rate law, I would write it as dc dt is equal to K times the concentration of reactants raised to the order of reaction. And in this case, since I have a first order reaction, that would be equal to 1. Reactants in our case, it would be drug concentration, okay? So therefore, dc dt is equal to K times C, and C is my drug concentration. Now, when the drug concentration increases with time, I will have a positive sign in my equation. When drug concentration decreases with time, I will have a negative sign in my equation. Now, in pharmacokinetics and in biology, many of the biological processes are described or approximated using first order kinetics. For example, drug absorption could be described using the positive sign in the equation, where the rate of change of drug concentration in the blood is proportional to the concentration of the drug in the GI. Similarly, the rate of drug elimination could be described by the first order equation using the negative sign, where and is a negative sign because with drug elimination, the concentration in the plasma is decreasing with time, right? And the rate of change of drug concentration in the plasma is proportional to the concentration of the drug in the plasma. So this is the most important difference between the first order reaction from zero order reaction. Recall that in a zero order reaction or in a zero order process, dc dt was equal to K independent of drug concentration. So this is the zero order. Now, unlike the zero order now, in first order reactions, the rate of change of the reaction is linearly dependent on the drug concentration. That is, and please pay attention to that, when the drug concentration is high, regardless of equation here, the rate of change is high as well, okay? When the drug concentration is low, the rate of change of the drug concentration with time is going to be low as well. This is very, very important. Also, for your information, equations that describe first order kinetics are commonly used to adjust dosing intervals and dosages in the clinic. Regardless of whether a drug follows a one compartment model, a two compartment model, or a three compartment model, we're going to discuss these compartment models later. Adjusting or calculating dosages and dosing intervals in the clinic quite frequently are using first order equations. Okay, now let's take a look at figure 12.4, which actually plots dc dt versus C. So here again we have the differential rate law. So dc dt is equal to K times the drug concentration. And in this case, because the dc dt declines, I must be having an elimination process, so I'm using the negative sign. And in this lecture, we are going to be describing first order elimination processes. Now, notice that when the concentration is high, let's say 100 here, dc dt is very high, it's 200. Please disregard the negative sign as that is included in the equation. So when the concentration is high, dc dt is high. When the concentration is low, let's say here, that would be maybe 5, the dc dt is close to 0. So again, we verify when C is high, dc dt is high. When C is low, dc dt is low. Also, we've plotted dc dt against the C. So the slope must be equal to negative k. So here, slope is equal to negative k, and from the best fit equation you can see that the slope is equal to negative 2. So therefore k is equal to 2. What would be the units? Now we've plotted dc dt against C, so the concentration units cancel out, and k must be having units of inverse time, as it is reported over here. So let us finish this figure. My slope is equal to negative 2, and therefore the rate constant must be equal to 2 with units of inverse time. Notice once more that k's are reported as absolute numbers. No signs, please, okay? Now, recall that in zero order processes, the rate of reaction is constant independent of concentration. Recall in lesson 29 that dc dt was equal to negative 3, right? Regardless of the concentration here. Here in first order, once more, high C, high dc dt, low C, low dc dt. One more important point that is quite confusing to students, especially at the beginning, is that the rate of change dc dt changes with the concentration, but it changes proportionally to the concentration, and most importantly, it has this change is described with a constant rate, or with a rate constant, okay? So we have a rate constant, but we do not have a constant rate of change of concentration with time. So again, we have a rate constant that describes the increasing or decreasing rate of change of concentration with time. Very, very confusing at the beginning, but hopefully by the end of this lecture and with a little bit of self-study, it should be clear. Okay, so we have already described all of these points in these 3 paragraphs. A special attention in the last one, which says that k is a constant, but the rate of change of the concentration with time is not a constant. Okay, so this could be, for example, elimination rate constant, but the rate of drug elimination with time is not constant. Okay, all right. So now, since the rate of change of drug with time is proportional to the concentration of drug remaining at each instant, a plot of drug concentration, let's say here concentration, per unit time should be an exponentially decreasing curve if we are referring to an elimination profile, of course. So this is what I am describing here. If I am to plot C against T, I will be getting an exponentially decaying curve. Okay, let's take a look. So here is exactly what I just described. For an elimination process, first order elimination process, C plotted against time is an exponentially decaying curve. And notice now that the slope is not a constant, because the slope, what is the slope? That should be C2 minus C1 over T2 minus T1, right? That is dc dt. We know that dc dt is not constant in first order processes, and this is what we have just described here. As time increases, these slopes become less and less steep. So essentially, when the concentration becomes low, the dc dt is also very low. When the concentration at the beginning of the elimination process is high, for example here, the slope will be very steep like that, okay? Because dc dt here will be very high, okay? So here the slope will be, let's say, something like that. So this would be my slope when the concentration is high, and therefore dc dt is high. Now notice that the concentration decreases, right? So as the concentration decreases, the slope becomes less steep. So the decrease as well, because the slope are representing dCdt. And dCdt is proportional to C. So when C becomes very, very low, dCdt is also becoming very, very low. The question now is, how do I describe this process? Well, it appears that the best fit equation here, since this is an exponential decay, is described by C equals to C0 times e to the minus kt, where C0 is my initial concentration and C is the concentration remaining. Okay, so here is that, let's say concentration remaining, drug concentration remaining. And of course, K is my first order rate constant. So let us take a look. So here we have the equation that best fits the first order elimination kinetics is equal to C0 e to the minus kt. If you are describing amounts of drug instead of concentration, then you can use A equals to A0 times e to the minus kt. And of course, A0 is again the initial mass of the drug in the body. And A is the amount of drug remaining in the blood or in the body. The question now that we need to answer is that, how do I determine K? We have seen that the slopes are variable. So the question is, how do I determine K? Now, in order to easily determine K, and especially graphically, we need to convert this exponential equation into a linear equation, and I can do that by taking the logarithm, by converting this exponential equation into a logarithmic equation. So if I take the logarithms on both sides of this equation, I get a ln C equals to a ln C0 times e to the minus kt. Now, we're using the properties of logarithms. The product of the argument here can be split into two logarithms. So this is equal to a ln C0 plus ln e to the minus kt. Now this can become, is an exponent, it can become a coefficient, and I could have negative kt times ln of e, but ln of e is 1, all right? So I end up with negative kt, and I have equation 12.7. So equation 12.7, ln c equals to ln c0 minus kt, is actually the same equation as C is equal to C0 times e to the minus kt, but in this case, this is a line. Y is equal to C minus n times x. So this m here is the slope, and this C here is the y-intercept. So I can determine now K from the linear best fit equation, from the slope of the linear best fit equation, and C0 from the y-intercept. Now we have to be careful here, because the intercept of equation 12.7 is equal to the ln C0, not C0, and therefore ln C0 is equal to the y-intercept, and therefore C0 is equal to the e to the y-intercept. Be very, very cautious, okay? So here, the same data that I have plotted in this case, exponentially decaying curve, I have now converted into logarithms, and here you have the best fit equation. So that would be ln c is equal to negative kt plus ln c0, all right? So this is my y-intercept, which is ln c0, and that's there. When time is 0, I have my y-intercept, ln c0. And my slope, negative k, is that one. So k is equal to 0.5. What are the units? Inverse time. Okay, so ln C0 now is equal to 4 point something, and when you raise it to the exponent, you end up with 100. Okay, simple as that. Now, to determine the half-life in first order kinetics, we understand again, as we mentioned in our last lecture, that the half-life of a drug is defined as the time at which the drug concentration reaches 1/2 of its initial concentration. That is when C is equal to C0 over 2. So I can start with my equation 12.6 and substitute C equal to C0 over 2 when time is equal to T half. And this is what I have here. Now, this is a multiplication now, so C0 and C0 cancel out, and I end up with a ln 1 over 2 is equal to negative KT half, and I can rewrite it as using the properties of logarithm, get rid of the negative sign there by inverting the fraction, make it a ln 2 is equal to KT half, and T half is equal to a ln 2 over K. Now, this is very, very important because in first order kinetic processes, you can determine the half-life of the drug without requiring knowing then the concentration of the drug in the body. All you need to know is K. So this is very, very important, right? You do not have to draw blood and determine the drug concentration. You only need to know K to figure out when the drug is going to come out of the body. All right, this is very, very important for our purposes here. So the T half again for the first order elimination process, a ln 2 over K. Obviously, this is a number, it's approximately 0.693. Let us now apply what we have learned so far. In example 24, we have a drug elimination after an IV, a single IV bolus administration in an adult male. C is the drug concentration in the plasma. So basically you have administered one IV bolus, and after 1 hour, 2 hours, 3, 4, 5, and 6 hours, you've drawn blood and you determine the plasma concentration of the drug as after 1 hour 18.62 and so on and so forth. And then you plotted this data in this graph here. What we have to answer here is identify the order of the kinetic process, calculate the initial drug concentration in the plasma, so that would be C0, right? Calculate the elimination rate constant, that would be the K, and calculate the elimination half-life of the drug, so that would be T half. Obviously, in order to determine whether the process is a first order rate process, you're going to have to plot this data as a ln C versus T, okay? Because remember, our equation now is a ln C is equal to a ln C0 minus KT. If this data, if the plotting of a ln C versus T is a line, that means your process is a first order process. Obviously, we have an exponential decay here, so this process is not a zero order process, but we still need to make sure that it is a first order process. So we're going to have to convert these concentrations as a ln C concentration. So basically for this one, it's going to be a ln of 18.62, okay? This is going to be for the ln C, that would be a ln of 14.94. So let's see what we have here. Exactly what I did over there, and when I plotted this data, so ln C now versus time, we got a perfect line, and this is the best fit equation. Now we know that our K is the slope, so therefore the K is 0.22, and I have units of inverse hour. Okay, the ln C0 is 3.144, and please be very careful, that's not C0, that's a ln C0, so I'm just going to write it here. A ln C0 is 3.1442, and therefore C0 is equal to e to the 3.1442. Okay, be very, very cautious here. Now, to determine the half-life, that's easy because I don't need the concentration to do that. That would be a ln 2 over K. Okay, simple as that, and essentially you're done. So here we are. This is my best fit equation, so the K is 0.22 per hour. And you could have determined K from the slope. Just be very cautious. You're not going to have C2 minus C1 now because you plotted logarithm, and you're going to have ln C2 minus ln C1 over T2 minus T1. Be very cautious with that, okay? It's a mistake that students make frequently, especially at the very early lectures. Now C0, a length C0 is 3.144, and therefore C0 is e to the 3.144, which is equal to the 23.2 milligrams per liter. And if you actually see the original plot, this is between 20 and 25, so 23 is a reasonable number. It's very accurate, of course, here because it is determined from the best fit equation. All right. Now the T half, that's easy now because that's a ln 2 over k, and that's 0.693 over 0.22, which is 3.15 hours. So 1/2 of the drug will be eliminated after 3.15 hours. So 1/2 of the C0, okay? Very nice. And now it is time for you to practice. In 12.5, I'm asking you to determine from the first order kinetics the units of the initial concentration. And here I'm asking you to determine the magnitude of the C0. Notice, be very, very careful. What you have over there is going to be a length C0, okay? And finally here, it's a real exercise actually, where you are asked to determine the percent decrease in the dose. This is a radioactive iodine that you needed to formulate as part of a therapy for a thyroidectomy. So obviously there was a thyroid cancer involved here. The recommended dose is 100 millicurie, and the decay of this radioisotope, or actually almost all the radioisotopes, is a first order process, and you need to determine again what is the percent increase in the dose if the pharmacist has prepared the formulation 3 days in advance. Okay, and you're given the half-life. So from this half-life, you can, of course, determine the K. This is the recommended dose. This is a very nice exercise. Enjoy it. And at this point, we have reached the end of this lecture. I would like to thank you for your attention. Until next time.